Okay, so today we will essentially be getting into the heart of representation theory, or at least trying to get to that. But before we reach there, some background has to be put up. So first, again something which all of you should already know, but a means of producing larger representations out of smaller ones is that of a direct sum representation. And for that, of course, you need a direct sum vector space. And let me just quickly remind you what that is. So let V1 and V2 be two linear vector spaces. Yeah. Then the set V1 direct sum V2 is defined to be, so this is a definition, ordered pair of vectors V1 comma V2 with V1 taken from capital V1, the vector space, and V2 taken from the second vector space. So this is a set, of course, of tuples, of couples in particular, of vectors. This becomes a vector space when you define how to multiply these elements by scalars, and the definition is sort of trivial. You just multiply each element, which of course belongs to a vector space, by alpha. So alpha V1 of course is an element of capital V1, alpha V2 is an element of capital V2. So this of course belongs to capital V1 plus capital V2, and you define the sum of two vectors, two elements of V1 plus V2 by this definition. Again, an obvious kind of definition, V1 plus V1 prime, comma V2 plus V2 prime. So in a direct sum vector space, each vector space gets to do its own thing. You multiply as if you are in the individual vector spaces, you add exactly the same way. So this is what a direct sum of two vector spaces is, and it is easy to show that V1 direct sum V2 is a linear vector space under these operations. So I'm not going to prove that for you, but you should, if you have not done this before, you should definitely take some time out and work this out, that this really is a linear vector space, that is, it obeys all the 8 conditions that a linear vector space needs to obey. Now, the reason why we are interested in direct sum vector spaces is that direct sum vector spaces provide us an easy way of finding out bigger representations from smaller ones. In other words, let's say we have a situation like this. Okay, so I hope if somebody asks to join, you people can admit, right? Can't you?
We can't, sir.
Oh, but then if somebody is trying to join from outside, which the sound right now seemed like, I can't see that person now. So if you see a caption like that, please let me know. Okay? Because I can't see my screen right now. I can just see what I'm showing you.
Sir, we won't even know if someone is trying to join. I mean, there won't be any notification. But if they join by ISA Kolkata ID, then they won't.
Yeah, they should join by ISA Kolkata ID. That's the basic idea. Sometimes people forget. Sometimes all that happens is that you may have two IDs. Most of you do, right? Most of you may have your own Gmail ID, and you may be logged into that, and you may have forgotten to switch.
We can't say if someone is trying to join, sir.
Okay, that's a bit of a problem. But anyway, I hope everybody here, this is a small group, everybody here should know that they can join by the ISA Kolkata ID. Okay, fine. So that's a problem which cannot be solved, so let's not worry about that. So Suppose we have two vector spaces V1 and V2 which carry representations, that is, let L1 and L2 be two representations of a group G on vector spaces V1 and V2. When we say L1 and L2 are representations, that means L1, L2 really are maps from G to the space of linear operators on V1. L2 is a map from G to space of linear operators on V2. And L1G and L2G, where L1 small g is an operator acting on V1, L2 small g is an operator acting on V2. So what we need really now is a definition of our operator LG for every G, which is going to act on, so L has to be, so I now want to define a representation of the direct product space. So I want to define an L which will take G to an LG for all, of course this works for all of the G belonging to capital G, where LG has to do something to an element of V1 plus V2. A typical element of V1 plus V2, as we said, is this. So I will tell you what LG does to V1, comma V2. And the most obvious way to define this is, since I already have an L1G which acts on elements of capital V1, I will an L2G which acts on elements of capital V2. What we will do, so we'll just define LG acting on V1, V2 this way. So I will let L1 do its own thing, L2G do its own thing, and they just act in parallel, one on V1, the other on V2. So that much is fine, but we need to check that this is a representation. Of course, we need to check that this is a linear operator, and that is sort of trivial to show, so I'm not going to bother showing that. It's also very trivial to show that this furnishes a representation, but just for the sake of completeness, let's try this. What happens when the LG1 and LG2 corresponding to G1, G2 elements of capital G act on a given vector of V1 plus V2? This, of course, is, as always, LG2 acting on V1, V2 first. That's going to be L1G1, sorry, L1G2 acting on V1, L2G2 acting on V2. So, just one word of warning, maybe I would have been better off saying G1, GG prime instead of G1, G2, because the 1, 2 up here, the one on L1 and the V1, these are really labels for the spaces. The labels G1 and 2 on the G's are simply labels of which group element you're talking about. Anyway, so this is what LG2 does, right? It makes L1G2 act on V1, L2G2 act on V2. Then you will apply LG1 on this resulting thing, which is going to be L1G1 acting on whatever is here. So L1G2 V1, comma, L2G1, L2G2 V2. And because L1 and L2 are representations, this definitely follows, right? This is the basic property which representations have. The same follows for L2 as well. And that, of course, is L G1 G2 acting on V1 V2. Now, since this is true for all V1 V2, this follows that LG1 LG2, the way we have defined L to be, obeys L of G1 G2. So L really is a representation. So what we have done here is we have figured out how to make a bigger representation, a representation on a higher dimensional vector space from two smaller representations. By the way, what are the dimensionalities? Say if the dimensionalities of V1 and V2 is N1 and N2 respectively, what is the dimensionality of V1 plus V2? So, so the question is, how big is this representation?
N1, N2.
N1, N2, the product?
Yes.
No, it's not. That you are actually confusing this with something else. It is of course related to the two dimensions, but it's just the sum. Why? Because notice that what can you write every element V1, V2 as? Every element of V1 plus V2, every element is of the form this V1 comma V2, and you can write this as I1 equal to 1 to N1 C1 En1 C1 E sorry I1 I2 equal to 1 to N2 sorry CI1, this is CI1 and CI2 E I2. And this immediately shows you that the basis for V1 plus V2 can be formed simply by this. Take E1 1 0, E1 2 0, all the way down to E1 N1 0. So this is the basis choice. This is of course a basis, it's not the basis, because as you all know, there are infinitely many different ways of choosing a basis. But this is a perfectly good basis choice. 0, E2, 2, 0, E2, and 2. So there are N1 vectors up here, each of the basis vectors of V1 with V2 0, with taking a 0 part from V2, and N2 vectors down here, where the V1 piece is 0. And it is easy to see that any vector V1 comma V2 can be written down as a linear combination of these vectors. Right? Just multiply this by C1. Okay, so maybe I will use different notations. I will write C1 and C2 here. Just to, that's important because you don't want to confuse the two set of C's. So you just put in C1 1 here, C1 2 here, and so on. And okay, the plus. Of course, when you're writing the basis, the meaning of the plus is, there is no meaning to this plus, it's just a comma here. But when you want to write down a given element, you can just multiply the first one by C11, second one by C12, and so on, and just combine them all together, you're going to get an arbitrary element. So basis is N1 plus N2 dimensional, not N1 N2 dimensional. This is a direct sum vector space. When you said N1 N2, I guess you were confusing this with the direct product vector space, which is a different ball game altogether. Okay, I hope this is clear. Is this?
Yes, sir.
Okay. So, of course, at any given stage, if anybody has a confusion, please unmute yourself and ask immediately. Okay. So now, what can we say about the matrix representations of a direct sum representation? As we know, to get to a matrix representation from an operator representation, so far we have been talking about an operator representation. To get to a matrix representation, what you have to do is that you have to choose a basis first. Now, of course, there are infinitely many choices of basis, but this is one obvious choice, the one which I've written down on the screen right now. So if we use this as the basis, then what happens? You're supposed to apply, take a given operator LG. So to find out the matrix representation corresponding to the group element G, small g of capital G, what you need to do is you need to take the linear operator LG, act on a basis vector. Now, what are the basis vectors? They are either of the form E1 I0 or 0 E2J. Let's look at this first. If it's acting here, what are you going to get? This is, of course, by definition going to be L1G, E1I, and L2G acting on 0. Now, these are linear operators, so this part, of course, simply gives you 0. And what about this part? This part gives the sum j equal to 1 to n1 d1g ji e1j, right? So all you are saying is since you already have a matrix representation for corresponding to L1, the matrix representation for LDG, at least when it's acting on the basis vectors of the first vector space, is sort of straightforward. Well, it's not only on the first vector space, you of course have to apply it on all the basis elements. So you also have to look at what will happen when things act on this. Let's call this I prime just to distinguish it from that I. And that of course is going to be 0. J prime equals 1 to n2 d2 g, the j prime I prime element of that, and acting on e2 j prime. So now if you want to use this information to write down the matrix representation for dg, what are you going to get? You are essentially going to end up with this. You are going to have a square matrix d1 g sitting here, which is an n1 by n1 dimensional, n1 by n1 dimensional matrix up here. Now, remember when you form the columns of this representation matrix, you take the coefficients, write them down a column. But when you write them down a column, the non-zero elements just stop at E1, N1. Notice that there is no contribution from E1, E2, N1, E2, 2, etc., etc. So you have all zeros down here. So it's very easy to see that ultimately you're going to get an N1 by N2 dimensional zero matrix, null matrix sitting on this corner. Similarly, you're going to get a, when you apply LG on E2I, you're only going to get a D2 here. Again, just N1, N2 by N2 matrix, and here you are going to get a, sorry, this is not N1 by N2, that's wrong. This is going to be, oops. N2 rows, N1 columns. This is going to be N1 rows, N2 columns. So, if you have a matrix representation of a direct sum representation, if you have a matrix version of that, it should be possible for you to find a block diagonal form like this. Just one D1 out here, another D2 out here, zeros everywhere else. Okay? Clear? Now, why do I say it should be possible and it is, and just possible? Why do I just say possible? Why not just say representation of a matrix has to be of this form, D1, 0, 0, D2?
If you choose a different basis of the vector space, then it might not be possible.
Well, it might not be is not the right word here, but anyway, you're right. The point is, I've chosen a very specific basis. I've chosen a basis in which the first N1 are basis vectors of V1, the next N2 are basis vectors of V2. Now, of course, if I form my direct sum space by starting from V1 and V2, this is a sort of natural choice to make, but I'm not bound to make this choice. So I could make some other choice.
Did Sir go offline?
Yes.
Does anyone have his number or can call him?
Oh, okay. No, no, I don't have it.
I too don't have his number.
Message him on Messenger. You might be able to see that.
I just did the same.
Okay.
I think he's having connection problems because before it disconnected, his audio was gone.
Yeah, but the problem is if he doesn't realize and continues the class.
No, but he disconnected intentionally, I
Oh,
guess.
he saw our messages on Messenger.
Okay, so I went offline. Since when?
A few minutes ago, sir. 1 minute at least max now.
Okay. So can anybody tell me where I was when I went offline? What was the last part?
The direct sum that it may not be the direct sum representation may not be diagonal always, block diagonal.
Okay, then we have not missed much. Okay, you have not missed much. So all I said after that was, it may not be block diagonal because you have chosen a different basis, but you could always choose this basis, and that means that every representation should be equivalent to a block diagonal form, or every matrix representation should be block diagonalizable. In other words, if you are dealing with a representation like this, a representation which has been built out of smaller representations like this, you should always be able to find some similarity transformation such that once you do that, the same similarity transformation, remember, on every one of the DGs, you should be able to bring the DG to this form. So although your DGs may not start out by this form, being this form, you should be able to find a similarity transformation which brings them all to this form. So that's what happens when you have a direct sum representation. Now this brings us directly to this concept, again a concept which all of you should be pretty familiar with, a concept which is very, very important, and that's reducibility. Let me get rid of this coffee cup, otherwise I'm definitely going to upset that. Okay, so let's start at a more abstract language first, at an abstract level first. An operator representation L. So remember, we are going to keep on switching between operator representations and matrix representations. Matrix representations may be easier to work with at a calculation level. However, operator representations are often ones which are easier to work with, okay, and prove results in. So you'll have to get sort of familiar with both. You know, one of the reasons why many group theory texts in physics tend to become very complicated books, or tend to have very complicated proofs, is simply because they stick to only matrix representations and don't switch between the two. So some results are easier in one way, some results are easier in the other. So if you sort of can move between the two seamlessly, it's actually much easier to understand the stuff than if you stick to any one of them. So we will usually talk about everything in both languages. On a vector space V is said to be reducible. Okay, this is one of the most important concepts that we are going to talk about today. If there is a non-trivial which is invariant under for all G. Okay. So this is our definition of reducibility. So if there exists an invariant subspace W, non-trivial invariant subspace W, then L is reducible. Now, what do I mean by non-trivial subspace? Of course, you all know this, right? Every vector space has two trivial subspaces. One is just the null vector, the other is the whole vector space. So if you leave them out, what you are saying here is that you must have a subspace W which is neither the whole space nor just the null vector, and it's invariant under LG for all G. That means no matter which small g you choose, the corresponding LG acting on W on an element of W will give you an element of W. So this is what reducible means. Now, if you have a situation like this, then what you can of course do is something like this. If you want, what kind of matrix representation will that lead to? If you have a reducible operator representation, what does that say about corresponding matrices? The answer is simple. You can now always choose your basis vectors in such a way that so let's say V is n dimensional, but W is n1 dimensional, and dim V is n, and because W is an non-trivial subspace, n1 is more than 1, or more than or equal to 1, and strictly less than n. It's more than n1 is more than 0, less than n, right? So now what you can do is of course choose the n basis vectors of V in such a way that the first n1 of them this first set, this gives us a basis of W, right? So of course you have all done enough linear algebra to know this. You can start with the basis of W and then extend it by adding more and more vectors which are independent to the vectors you have already chosen until you end up with a basis for the entire space, right? So if anytime I'm saying something unfamiliar, please interrupt, but I'm pretty sure this should be familiar. So if you choose a basis like this, what should the matrix representation for DG look like? Again, things should be pretty simple. If you start, so how do you form the matrix representation? You just apply LG on E1, E2, En1 up to all of these. And when you apply LG on E1, what happens? Remember, W is invariant under LG. What that means is LG E1 has to be an element of W. So when you actually expand it out in this set of basis vectors, you are going to get you are possibly going to get a non-zero coefficient only from E1, E2 up to En1. There can be no contribution from the other basis vectors, right? And that happens not only for E1, it happens all the way up to En1. So what you will get is a non-zero matrix here, which is n1 by n1 dimensional. And down here, you are going to get zeros, only zeros. So that's n minus n1, other rows left, and n1 columns, right? So what can you say about the other piece? D2. Of course, if you apply LG on En1 plus 1, En plus up to En, that means there are n minus n1 vectors left, you will get a n minus n1 times n minus n1 square matrix down here. But what can you say about these coefficients? Yeah, this is a question that I'm asking you. What should you be able to say about this?
It can be anything, right?
Okay, that's good. The point is there is no reason to presuppose at this stage that these are also going to be 0. Right? Just to remind you, if you started with a direct sum vector space and played the game, you would get a D1, D2, which are both individual representations on their respective vector space, and you had zeros here. This is the direct sum case. And here we are doing something different. We are starting with a vector space V. I have no clue whether it's a direct sum of two smaller vector spaces or not. I don't care right now. I have just found out that this V has an invariant subspace W, which means all the LGs acting on W give you elements in W. And what can I say about the corresponding representation on V? What I can say is definitely this. You are going to get some square matrix D1 N1 by N1 sitting here. You will get zeros here, definitely. But since you do not know that when LG acts on En1 plus 1 or En1 plus 2 and so on, you are going to get an element which is spanned entirely by these. You might get something outside. You may get coefficients here. What that means is you will get, in general, a non-zero rectangular matrix, n1 rows, n minus n1 columns here. So this is when this happens. So how do you relate this to what we said a while ago? We said if it's a direct sum, you are going to get this form. Here what we are saying is, okay, I don't care whether the vector space V is a direct sum or not. I just started with the V. I found an invariant subspace. I find that if you do this, you are going to get a form for the matrix representation which sort of resembles a direct sum form, but not exactly, because there's a non-zero C sitting here. Okay, these of course will depend on G, and this C will also depend on G. Now I will leave this as an exercise. In this case, what can you say about D1, G1, D1, G2? Note that here what you know is DG1, DG2, because I know that this D is a matrix representation, right? It's a matrix version of an operator representation which is living on the vector space V. We know that this will follow. What can you say about this? Any ideas? So this is where you start from. From that, of course, you can say that this is correct, and then just play with the matrix forms like this. And then you can immediately find out what will happen here. And there are no real prizes for guessing this one. This is going to be D1, G1, G2. You can easily check this. So that's one part of the exercise. Yeah. Any questions? I hope everybody knows how to handle block versions of matrices, how to multiply block matrices and so on. Yes or no? Have you ever done this?
Yes, sir.
Okay, so you should be able to work this out pretty easily, that this is going to follow. But what can you say? This is sort of trivial as well. It's easy to understand that after all, W is sort of insulated from the outside, from the rest of V, as far as the action of all the group elements are concerned. So if you're just looking at the action of capital G, then W can be taken to be as your vector space. You don't have to worry about the rest. So it's easy to see that what the LGs do to W should give you a representation of the group G on W, which means of dimension n1. But what can you say about D2? What is this? This is something which is easy to work out just by using the block form of the matrices. But I will leave you to worry about or work this out. This is what follows. That both D1, D2 actually give you representations of smaller dimension. N1, one with N1 by N1, the other with N minus N1 by N minus N1. It's easy to see why W is a vector space which carries a representation and hence gives you an N1 dimensional representation. It's not so easy to see directly why the complement space also should give you a representation, especially given the fact that the complement space is not necessarily invariant under the action of LG. Okay. So this is something which I will leave you to worry about. It happens. You can easily work out that this is true. But what is important? Let me just put one thing here. What is very important is this. Then we say that the representation is of course reducible. Did I actually define reducibility? Yeah, I did. Good. I just forgot about that. Then the representation is incompletely reducible. It is reducible, but this kind of reducibility is called incomplete. The complete reducibility would be reducible if there exists a basis in which each dt in other words, basically you have two subspaces whose direct sum forms this whole subspace and each subspace is invariant under the entire action of the group. If this happens, remember this has to happen not for one group element, that would be rather trivial, but this has to happen for every one of the group elements, for all G belonging to G. If this is the form, then you say that the representation is completely reducible, in which case you just can go around and say, okay, we actually started with a big vector space, but really we had two smaller vector spaces whose direct sum was this V. And so what we really had all along was this direct sum representation. Is this clear to everybody? So this is what complete reducibility means. Okay. So we have two versions of reducibility, incomplete and complete. The important theorem that we have here is the distinction here is unimportant for finite groups. So that's really not a theorem, and nobody writes this as a theorem in a math text. But this is really what will follow. That although I took pains to define what defines a reducibility and what defines complete reducibility, the distinction between reducibility and complete reducibility is unimportant for finite groups. And there is no reason why you have to worry about incomplete reducibility as long as you're dealing with finite groups. With infinite groups, there can be an issue especially if the infinite group is not compact, but we are not going to tackle infinite groups right now. We are going to talk about them a lot later. So let's now stick to this. Why is the distinction here unimportant? Because you have the real theorem. This really was not the theorem. This was a crazy way of saying that. The real theorem is a unitary representation of a group G on, of course, if it's an unitary representation, has to be on an inner product space, right? Without an inner product, you can't even define unitarity. This is a theorem. It's completely reducible. If it is reducible, sorry, I list out the most important point here. It's not completely reducible. It's completely reducible if it is reducible. So this is the real theorem, and we are going to talk about a proof of this theorem soon. But before we go there, can anybody tell me why this statement essentially means this? Yeah, tell me. The actual theorem is the one in blue. The cartoon version that we have is the one in black. So can you tell me why the two are sort of the same statement?
Any representation on a finite group is equivalent to unitary, and if it's reducible, it's completely reducible. That's right.
Great. So just the other day we studied this, that every representation of a finite group on an inner product space is equivalent to a unitary representation. It's not necessarily a unitary representation, but you can always find an equivalent unitary representation. And since every unitary representation, if it's reducible, it's completely reducible, then you start with whatever representation you have, you go, if it's reducible, you can go over to its corresponding equivalent unitary representation. That will also be reducible. That's actually something you have to prove. But once you have proven that, it is completely reducible. So your original thing is equivalent to a completely reducible case. So there actually does not exist incomplete reducibility in finite dimensional groups or representations of finite dimensional groups. Okay. So what we need is a proof of this statement, and the proof really is rather simple. So how do you prove this? Of course, when you are saying it is reducible, that means if your representation is on a vector space V, there must exist a subspace V1 of V invariant under LG for all small g belonging to capital G. Is that okay? That's what reducibility means, right? There has to be an invariant subspace. Okay, invariant, that actually is a non-trivial invariant. That's something which I may not remember to say every time, but that's important. So now we can define another subspace, V2, which is defined to be the orthogonal complement of V1 V1. So V1 perpendicular. What does that mean? It means that you take all the elements for V such that V2 is orthogonal to small v1 for all small v1 belonging to capital V1. So essentially you collect all the elements of capital V which are orthogonal to everything in capital V1. Now we can easily show that this is a subspace. That this is a subset is easy. We can easily show that this is a subspace of V. Okay, I will urge you to figure out a proof of that. Is really rather trivial. Nothing much to do here, but still. Okay, so we have this. Now what we need to prove is this, that V2 invariant this is what we need to prove. That will later leave us with two subspaces V1 and V2, and we can easily show that capital V is actually isomorphic to the direct sum of V1 plus V2, and both V1 and V2 are actually invariant under LG. So how do you prove this? And this is where the unitarity comes in. To prove that V2, let's say capital V2 is invariant, what we need to do is start with a vector in capital V2, let's say small v2, apply LG on that and ask whether this is orthogonal to every V1 belonging to capital V1. So how do we go about showing that it is? The answer is simple. This is an inner product, right? And because it's an inner product, and because of the definition of an adjoint operator, I can always write this as L dagger G V1, comma V2. So I can move the LG from the second element to the first element. Of course, when you do that, L changes to L dagger, right? That's the definition of L dagger. This has nothing to do with a unitary representation or anything, right? It's just how L dagger is defined. But now comes the important thing. If you have a unitary representation, then L dagger G is simply LG's inverse. But what's LG's inverse? It's L of G inverse. Right? Because this is a representation. So that's a pretty straightforward result. Now, can you tell me why this tells you that this must be 0? Go ahead, I am waiting for the answer.
Because V1 is itself an invariant subspace. So LG G inverse is actually an element belonging to capital G. So
exactly. Good. Great. So G inverse is an element of capital G. So LG inverse acts on capital V1 invariantly. That is, LG inverse acting on any element of capital V1 will give an element of capital V1. So this thing here belongs to capital V1, and by default small v2 is orthogonal to every element of capital V1, so this has to be 0. But what does it tell you? It tells you that you start with any element of capital V2, apply LG on that, you get an element of capital V2, right? LG V2 must belong to capital V2, because capital V2 is by definition all these vectors which are orthogonal to every element in capital V1. So what we have managed to prove is not only V1 was already known to be invariant under LG, V2 is also invariant under LG for all G belonging to capital G. Now the final steps of the proof is sort of trivial, or it's more or less bookkeeping. What you really say is, if you have any vector V any vector for any small v belonging to capital V, small v can be written down as v1 plus v2, where v1 belongs to capital V1, v2 belongs to capital V2, and then this helps us define a map from capital V to V1 direct sum V2 by saying take V, map that to V1 comma V2. By the way, why is this map a well-defined map? All I'm saying is give me small v, any vector in capital V, I can break it up into a vector in capital V1 plus another vector in capital V2. And then I'm saying I can map capital V to an element of V1 direct sum V2 just by saying V, small v maps to this pair of V1 comma V2. Why is this map at all well defined? Am I still there? Okay, I think I am.
It can be shown actually that the decomposition is unique.
Okay, that's a very important point. You have to be able to show that this decomposition is unique. That is, if you had a decomposition like V1 plus V2 is also the same as V1 prime plus V2 prime, where V1 prime and V2 prime also have the same property, that V1 prime belongs to capital V1 and V2 prime belongs to capital V2, then V1 has to be the same as V1 prime, V2 has to be the same as V2 prime. The proof of this is very simple. It's really this: V1 minus V1 prime has to be V2 prime minus V2 then, right? Now let's focus on the vector on the left, V1 minus V1 prime. Which vector space does this belong to?
V1.
But it must also belong to V2, right? Because it's equal to the vector on the right.
Yes. So it's identity.
You mean 0, right? Identity of...
Yeah, 0.
Why do you say so? Why are you so sure that the only vector which is common to both the subspaces? We made no such statement, right? Why are you so sure that the only vector which belongs to both is the 0?
This is because 0 dot 0 is 0. So it...
I guess you are trying to say the right thing, except that you are saying just the opposite. 0 dot 0 and 0 is still here.
Like, because...
Sorry, you're breaking up. I couldn't hear you.
Because every element of V2 is perpendicular to V1, right?
Yeah.
So we have an element which belongs to both V1 and V2.
Yeah.
So therefore it must be the 0 vector.
How would you prove that? You're right. I guess you are giving me the right argument in the right order, except that you are dropping the clinching step. The clinching step simply is this, that this element, whatever it is an element of V1 which is orthogonal to every element of V1.
Yeah.
And the only element of a vector space which is orthogonal to every element of the vector space, that's the part of the definition of that's actually called the non-degeneracy condition for the inner product. That if you have an element which is orthogonal to every element of a vector space, it has to be 0. So that's why this has to be 0. And if it's 0, of course on the left it's 0 on the right. So that means this is unique, this decomposition, which means this is a well-defined map, and you can easily show that this map is a linear space isomorphism. Why is that important? Because once you have shown that this is a linear space isomorphism, you can now directly show that your vector space, your representation L on V can be directly decomposed into smaller representations L1 and L2 on V1 and V2, such that L is really nothing but a direct sum of L1 and L2. And of course, if this is the case, then you have complete reducibility. So at least for finite dimensional groups, the distinction between complete and incomplete reducibility does not matter. Okay. So I have half an hour sort of left. So what I'm going to do, I'm going to make a start on what is going to be the central result in representation theory, or okay, not the central result, but what something which directly leads to central result. I should be able to complete this today. Let's see. If not, we will continue the next day. These are the famous or infamous Schur's lemmas. Okay. Now, Schur's lemmas have a bad reputation, especially if you read physics books which deal with group theory, or chemistry books which deal with group theory. Of course, most chemistry books which deal with group theory don't even mention Schur's lemmas. They just mention perhaps in passing that there is something called Schur's lemma in mathematics which gives you the orthogonality theorem in the end. And most chemistry books don't even give you the orthogonality theorem, it just gives you the direct consequences of that so that you can calculate results. Even in physics textbooks, Schur's lemmas, if at all mentioned, are usually mentioned in terms of matrix representations, which is one of the reasons why I said it's good to be conversant with both languages, because Schur's lemmas are really very, very simple things to state and prove in the operator version. And from that, the matrix version immediately follows. The proof in the matrix version is sort of lost in lots of I, J, K indices. So we will talk about Schur's lemmas in the operator version. And for this, we need a definition first. We need a definition which actually on the face of it has nothing to do with group theory or group representations, but as you will soon see, and it should be obvious from the statement, that is something which is related to representations. But this is something called an irreducible set of operators. So what is the definition? The definition goes this way. A set of linear operators on a vector space V is said to be irreducible if the only subspaces which are invariant TIs, that is, it has to be invariant not only under T1 or T2, it has to be invariant under T1, T2, T3 all the way up to Tn. Now, it would be rather tempting to say that there are no invariant subspaces under T1, T2, T3, Tn, but that of course will be trivially wrong, because as you know, every vector space has two subspaces always, One of them is the null space, which has only the null vector, and that's obviously invariant under the action of linear operators. If you have only the null vector, T1, T2, T3, Tn acting on the null vector will give you just the null vector. And the other subspace which V always has is V itself, and that of course is invariant under T1, T2, T3 up to Tn. So you can't say it has no invariant subspaces, but what you are claiming is the only subspaces of V which are invariant under the action of all of the Ti's are the trivial ones. So if that happens, then you say that the operator is an operator set of operators, not an operator, but the whole set of operators is an irreducible set of operators. So this is the crucial notion for what is going to follow. Are there any questions about this? So why is that important for us? The reason why that is important for us is simply this. Okay, maybe I did not even define this. I defined the situation when a representation is reducible. What I did not define is what you mean by an irreducible representation. One of the important reasons for that may be subconscious, maybe simply because I find it very difficult to pronounce irreducible representation. It always sounds similar to me. So I tend to avoid saying that as much as possible. So to an irreducible representation, but an irreducible representation is simply this. A representation is reducible if there is a invariant subspace. If there is no such invariant subspace other than the trivial ones, then it is irreducible. So the operators LG corresponding to an irreducible representation of a group on a vector space V constitute an irreducible set of operators on V. So while the notion of an irreducible set of operators exists in linear algebra and has nothing necessarily directly to do with group theory, the reason why we are interested in them, and frankly the reason why anybody is interested in them really, is that in group theory, when you're talking of irreducible representations, the corresponding operators of course give you an irreducible set of operators on V, and that's the real reason why we are so focused on these irreducible set of operators. And although I did not say so today, but I'm pretty sure all of you know this, and I have already said that earlier, or I've definitely said that earlier when I was teaching group theory last time around. The reason why we focus so much on reducible and irreducible representations is what we saw right now. If you have a reducible representation, at least for a finite group, is equivalent to a completely reducible representation. That means you can break up the representations into smaller pieces, and you cannot do that only if the representation is irreducible. And hence, you can start with a reducible representation, break it up into smaller pieces, keep on going until you cannot find any smaller piece. And that means any big representation can be thought of as being made out of many small representations, at least smaller representations. And smaller things are easier to understand than bigger things. So this is the basic philosophy why we really love irreps. Okay, the good thing is irreps is a lot easier for me to pronounce than irreducible representation, so I'm going to just call them irreps from now on. So with this background, let's now state the two lemmas. The lemmas are about irreducible set of operators, but of course they will directly translate to properties of irreps in a group. So lemma 1. There are two lemmas. Schur's first lemma goes this way. Let Ti1 I equal to 1, 2, dot, 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 n, and Ti2, again I going from 1 to n, be two sets of irreducible operators on vector spaces V1 and V2 respectively. So of course I'm not claiming that V1 and V2 are necessarily different vector spaces. All I'm saying is they can be. And you have two sets of irreducible operators on both of them, both with the same number of elements. So what happens if one has more than the other? All you have to do is just cut down the larger one, throw away some until they have equal number. Well, if a set of operators is irreducible, then any subset is also irreducible. That's sort of easy to show. And let X be a map from V1 to V2. Sorry, I should use the same notation for both. So such that, okay, X be a linear, X of course is a linear map. Unless otherwise stated, all maps we are going to talk about between linear vector spaces are linear, such that X Ti1 is Ti2 X, where I goes from all over 1 to and all the way up to n. Let's go on to the next page. Then, okay, before I state what the lemma is, let me just depict this pictorially a bit. Suppose this is a pictorial representation of your vector space V1. This is V2. And let's say I have an element here. And if I apply X on that, oops, that's the problem of having a, yeah. So we have a map X which takes an element from V1 onto V2. What this is telling me is something like this. Suppose we apply the operator T1 or T2 or anyway Ti1 on that first, on this same element. So I get Ti1, it moves you within V1 to a new point. Of course, what I can do is after I get this, I can apply X on that and I will land up here. What this is telling me is simply this, that if I first apply X to go to V2 and then apply Ti2 to go to the final result, the result will always be the same as applying Ti1 first to move within V1 and then applying X. So mathematicians have a name for this kind of stuff. They say that the diagram commutes, which essentially means that which way you go, you get the same result. By the way, the diagram commutes and the operators commute. It's very tempting to say X commutes with a Ti. But But you can see that that's wrong, right? Why is it wrong to say X commutes with Ti?
Because there are two TIs present, one in
Yeah, so right, the two TIs are not the same TIs. One acting on the vector space V1, the other acting on the vector space V2. So it's really wrong to say X commutes with Ti1. The correct language is X intertwines with the Ti. So we will not use that language very much, but that's a kind of language which people use in braid groups and stuff like that. But if this happens, so remember we have not got to the lemma yet. All we have done is set up the lemma. That what we have, just to remind you where we were, we have two irreps or two set of irreducible operators on two vector spaces V1 and V2, and you have map between the vector spaces which intertwines between the two sets of operators, two irreducible sets of operators. And now comes the actual lemma. Then X, then either X is 0. Well, of course, if X is 0, which means maps every element of V1 to the null vector in V2, then it's easy to see that X Ti1 will be equal to Ti2X for all I, right? That's sort of trivial. But what is not so trivial is this result. Either this is 0, or if it is not 0, then X inverse must exist. Okay? So that's the theorem. Or sorry, that's not the theorem, that's a lemma. I'm not sure whether I have asked you this in this class before, or this class meaning this one and the previous third year class. What do you think is more important, a lemma or a theorem? Okay, that's a question. What, in your opinion, is more important? Is a theorem more important or a lemma more important? Or let's put it this way. A named lemma, something which you name after somebody or some phenomenon, usually after somebody. That's what mathematicians usually do. They name their lemmas after people. Typically the discoverers, at least if you know who discovered them. So, once again, if there's no response, I'm worried whether I've been cut off.
No, sir, you're here.
Yeah, I'm here, so I want an answer.
Sir, I cheated. I googled it.
Okay. Oh, you googled it. Is that on Google as well?
Yeah, I just type in what is more important, theorem or lemma.
Oh, and what did Google say?
It said theorem. Essentially, it says lemma, a minor result whose sole purpose is to help in proving a theorem.
Right. So if you look at the definition, then you will get the wrong impression. Because the definition says lemma is a minor result whose sole purpose is to prove a theorem. That's true. However, when do you bother to name a lemma? You can have a lemma as part of proving a theorem and you then move on. Such lemmas, of course, are really part proofs, not really that important. But lemmas which are named after people or events or things, why did you bother to name them? Simply because you want to use them over and over again. Because they can be used over and over again. Okay? A single lemma can be important in proving many theorems. That's why you bother to name them. Otherwise, you wouldn't have bothered to call it something. You would have just said, okay, this is step A, step B, step C, and then you go on to the theorem. Okay? So the Google version gives you the definition of lemma and theorem, but frankly, a lemma which you bother to name after somebody is really more important than theorems. Why? Because the only reason why you bother to name the lemma is because you are going to use it over and over again to prove multiple theorems. If a lemma is only useful to prove a single theorem, then why bother naming it? Then it's part of the theorem's proof anyway. You get my point?
Yes.
The two Schur's lemmas are actually very, very important because they help you to prove a whole host of results in representation theory. Not just one result or two results. Okay. So there are only two lemmas, but they will recur over and over again in various versions. That is precisely why Schur's lemmas are actually central results. The orthogonalization theorems are actually consequences. So the relationship between a lemma and a theorem is not, well, not exactly the same as a relationship between a theorem and a corollary. A corollary is something which sort of follows trivially once the theorem is established. But in a way, it's sort of similar. What a corollary is to a theorem is to a lemma, in that sense. Okay, having gone there, let's come back to this. This theorem, or sorry, this lemma essentially says this, that if you have an intertwining X, an operator which intertwines between two irreducible set of operators. Okay, can I just hold on. Bishubda, আমি তো একটু পরে ফোন করছি, ক্লাসে আছি, unless it's an emergency. Emergency না তো? Okay. Hey, 40 minutes? Okay. Okay. So then either x equal to 0 or x inverse exists. So let's prove this. The proof, this is where the linear algebra version comes in very, very handy. For the proof, you just need two subspaces of V1 and V2 respectively. Yeah. I saw an alarm bell right now. Heard one, sorry. I don't know what that was for. So, you know what okay, you know these two subspaces, right? Kernel of X, which is all elements V1 belonging to V1, such that X V1 Of course, when I say 0, I really mean 0 of capital V2, but that's something we will sort of take for granted. It's obvious which 0 you talk about. An image of X is, of course, all V2 belonging to capital V2 such that exists V1 belonging to capital V1, where V2 is capital X V1. Okay. Now, I hope everybody knows that kernel of X and image of X are subspaces. That is, Ker-X is a subspace. They are of course subsets, but they are subspaces. Is this known to everybody? The kernel of X is a subspace of V1? Okay, I am assuming it is. And image of X is a subspace of V2. These are very easy things to prove anyway. Even if you did not know them already, they would be trivial to prove. Now, let's prove that they are not only subspaces, they are invariant subspaces under the conditions of this lemma. How do you prove that? Invariant under, when I say invariant, I mean invariant under T1, T2, T3, Tn. Which Ti depends on which space you're talking about. So let's focus on the kernel first. So if V1 belongs to Ker-X, what we want to show is that under the action of for every I equal to 1 to n, that is under the action of every one of the T1, 1, T1 to T1n, the vector that you get when you apply T1i on V1 is in the kernel. So how do you do that? To check whether a vector is in the kernel or not, all you do is apply X on that. But now I have the intertwining property, right? This is that's because xti1 is ti2x for all the i's. And what does this tell you? What is xv1? Yes?
Zero vector.
Here is a zero vector, and Ti2 acting on zero vector has to be the zero vector. Okay, zero vector of V2, but let's not bother saying that, right? So that means also belongs to Ker X. Subspace under each one of the Ti's, right? T11, T1n. Is it okay? So now what can you say? We have already said that T11 to T1n form an irreducible set of operators on V1, and we have now found that for this operator X between V1 and V2, we have a kernel which is invariant under T11 to T1n. So what can you say about kernel of X? There are only two choices, right? But a subspace which is invariant under the action of every one of a set of an irreducible set of operators, has only two choices. The only ones possible are the trivial subspaces. So either Ker X is 0, that is a singleton set with only the null vector, or Ker X is V1, right? Are you with me so far? If any confusion, please tell me. But now we have two cases. What does this tell you about X? Yes? If Ker X is V1, what does it tell you about X?
A zero map.
It has to be the null map, right? Because then it takes every element of V1 and maps it to 0. Else, okay, if not, what does it say about X? About X? Either this or Ker X is the null vector alone, singleton set. What does it tell you about X? X is, if the kernel of a map is the null vector alone, what does it tell you about that map? If the kernel of a linear map is the null vector alone.
It's
Yeah.
Invertible.
Is
it's
what?
one-
What does it say? Is 1-1 or invertible? Yeah. This is basic linear algebra. If the kernel of a map is just the singleton set. By the way, this is very similar to another result we have in group theory. If the kernel of a homomorphism is just the identity. Essentially the same thing in two different guises. What is that? Well, you all know this, I'm sure. It's 1-to-1. That's all you can say. You can't say it's invertible. You can say it's in 1-to-1. The proof is of course trivial. It says basically that if xv1 equals xv2, then x acting on v1 minus v2, this is linearity, has to be 0, which implies v1 minus v2 has to belong to kernel of x. And since kernel of X has only the single element 0, this implies V1 has to be equal to V2. So the only way you can get different results when you apply X is start with different vectors. That's 1-to-1ness. Okay. That's not the full lemma. That's just a statement that I've got from kernel of X. But there's another subspace that we were talking about. This is a subspace of V2, remember? Not okay, that's not wrong to say also invariant. What we can say is image of X is invariant under, it's wrong to say it's also invariant simply because it's under a different set of operators. That's a statement I'm making. The proof, well, proof is trivial or very similar to what I've already done with the kernel. You have to use the intertwining property and prove this. It's straightforward. But now what do you conclude? You conclude that either of course this zero set and the zero set that we had for our kernel of X are different sets, right? This is 0 of V2. That was 0 of V1. Or X has to be V2. Sorry, or image of X has to be V2. Okay? So now, image of X is this one. What does it tell you? If this were the case, what does this tell you about X?
Null map.
It has to be a null map. So that means both ker X equals V1 and imx the 0,2. This is, both of these imply only one thing, that X is 0. But if X is not 0, then ker X has to be this, which I've already seen that X is 1 to 1, and imx has to be V2, which implies X is what?
Invertible.
This alone says X is onto.
Onto.
Both together, and they have to hold together now. One holds from the fact that the set T11, T12 is irreducible. The other holds from the fact T21, T22, T2n is irreducible on V2. But when you have both of them together, you end up with X is 1 to 1 and onto, so X inverse exists. So that's the proof of Schur's first lemma. So if you have some time, maybe 10 minutes, I will just finish lemma 2 and its proof and then stop today. Is that okay with everybody?
Yes.
Yes, sir.
Okay. Because I don't want to leave this hanging in the middle. So lemma 2. Lemma 1 was about two irreducible sets of operators on two vector space and an X which intertwine between them. And lemma 2 is about one set, so that's why I don't have a 1 or 2 written up there, because it's just on one vector space. Be an irreducible on a vector space V. So there we have two irreducible sets of operators and a vector and two vector spaces, and X between the two X was a linear operator between V1 and V2. But now X here is a linear operator on V, such that, well, xti is tix. So this really is commutation. So you have an operator X which commutes with every operator of a set of irreducible operators on a vector space, then if this happens, then X is a multiple of the identity. So an operator which commutes with every operator in an irreducible set of operators has to be a multiple of the identity. This is Schur's second lemma, a very, very important lemma. In fact, this is going to be critical. Both of them are going to be critical for proving various results that we are going to use in group theory. It says something very simple. It says that the only operator which commutes with every one of an irreducible set of operators has to be a multiple of the identity. Of course, if it is a multiple of the identity, the converse is that's not the trivial, right? Any multiple of the identity commutes with every operator. So that's really trivial. But what it's saying here is that the only operator which commutes with every element, every operator in an irreducible set of operators is a multiple of the identity. So how do you prove that? Well, for any given x, not for any given x, of course, there is only one x here, but you can just define a new operator, x prime with a lambda suffix, for the timing, this lambda is any number. Now, I, of course, is the identity operator. So given this definition, it's very easy to see that because x commutes with every one of the TIs, x prime lambda, for whatever lambda you define, has to commute with every one of the TIs, right? So lemma 1 implies, what does it tell you about x prime lambda? Go ahead. This is lemma 2, of course, but lemma 1 we have already proven. And in lemma 1 we have two vector spaces v1 and v2 and a map between the two spaces. But remember, we never said that v1 and v2 have to be distinct. v1 and v2 are two vector spaces, right? So here v can play the role of both v1 and v2. And now what do you have? What would lemma 1 say about this? About the x prime lambda?
0 or invertible.
Yeah, right.
So 0 is the identity thing. The x is equal to lambda I.
Yeah. If it's 0, then x is equal to lambda I, right?
Yeah.
But the point is, what we have to show is that there is, look, either this is true or this is true, right? But nobody says that this has to be true. If you can show that this has to be true, nobody has said yet at least that this first thing has to be true. You just as well say, okay, fine, x prime lambda inverse exists. And then you no longer have this result that x is lambda I, right? But you have to show that there exists at least one lambda for which x prime lambda is 0. That is, the inverse does not exist. Now this really is trivial from whatever you have learned about linear algebra from almost the very beginning of linear algebra. How do you show that there is at least one lambda for which x prime lambda inverse cannot exist? Yes?
the eigenvalue.
Yeah. So the point is, let lambda be an eigenvalue of x. Then there exists a v, let's call it v lambda, not equal to 0, such that and what does this tell you? This tells you that the kernel of x prime lambda contains at least this v lambda. In fact, it contains not only v lambda, it contains all its multiples. In fact, the kernel of x prime lambda in this case is nothing but the eigenspace corresponding to the eigenvalue lambda. The one thing that we know about an eigenspace is that it cannot be just the zero vector, because if that were the case, then it would not be an eigenspace at all. So kernel of x prime lambda is not just 0, which means x prime lambda is not 1 to 1, and then the only option left for that particular lambda for us is this. Is it okay? So all we have to show is that there is a non-trivial eigenspace for every operator, but this is something which you know already, right? Every operator on a vector space has a non-trivial eigenspace. Is that okay with everybody? At least on a finite dimensional vector space? At least one non-trivial eigenspace? You know the proof of that, right? Every operator on a finite dimensional vector space has a non-trivial eigenspace. That is, has at least one eigenvalue and corresponding eigenvectors. Is it okay? Do you know the proof of that?
Sir,
Yeah.
one question. Why couldn't we proceed by using the determinant, like I know we are using the linear operator representation here? But if we know that lambda is an eigenvalue, then we can easily see that determinant of x prime lambda is 0.
Yeah.
And then can't we conclude that it is non-invertible?
Well, actually, you don't have. That would be, first of all, that would be an overkill, right? The best. Look, that you are using a more complicated result to prove something more fundamental. When is an operator invertible? It has to be 1 to 1 and on to for that to happen. You can show it's not on 1 to 1. Invertibility goes out of the window. End of story. So you don't have to go to a more complicated result. What you are using is a result which follows from this definition. That the matrix corresponding to a singular operator, a non-invertible operator, happens to be a singular matrix. It's called a singular matrix simply because it corresponds to a singular operator, and it has a determinant which is 0. However, let me just point out that what you said right now is actually part of the proof that an eigenvalue exists. Right? All you do is determinant of x minus lambda I equals 0. What kind of an equation is that? What kind of an equation is that?
Characteristic equation.
No, what kind? It's called the characteristic equation, fine. But what kind of an equation is that? What type of equation? Come on, the equations can be classified in various types. It's not a differential equation, right?
Oh, it's
Polynomial.
It's a polynomial equation.
Yeah,
And the fundamental theorem of algebra guarantees that every polynomial equation has at least one root in the space set of complex numbers. Do you know that? First of all, do you know what that is called the fundamental theorem of algebra? More importantly, do you know the proof of that?
I
If
just
you
know the statement.
if you don't know that, you should find out. At least there's a beautiful proof using complex numbers, a complex analysis of this result, which is pretty straightforward, which just starts by assuming that a polynomial does not have any zeros. And so if you were to divide dz by this polynomial, this result, if you take 1 over this polynomial, then it will have no poles, and show that that's inconsistent with Cauchy's theorem. So this is pretty straightforward and rather beautiful proof. You should all know the proof. It's a very important central result in maths. But this guarantees here that because data of x minus lambda I equals 0 is a polynomial equation, it has at least one root. Because it has at least one root, it has an eigenvalue, so a non-trivial eigenspace exists. And that is what we used here. That since if you are using the eigenvalue, the point is, when we say something like this, let lambda be an eigenvalue of x, we actually assume that there is an eigenvalue for x. So to complete the proof, you should, or this is a result which of course we don't have to prove here because it's standard result in linear algebra. But without this result, we should not have been able to make this statement. But let me just summarize what we have done here. We have essentially ensured that these two theorems, these two lemmas, lemma 1, which says that an operator which intertwines between two irreducible sets of operators on two vector spaces, not necessarily two distinct vector spaces, but between two vector spaces, has to be either 0 or invertible. And lemma 2 focuses on what happens when the two vector spaces are the same vector space, and you're talking of only one set of operators, one irreducible set of operators. Then x has to be a multiple of the identity. Or, well, why not say or 0, by the way? Can't x be 0? This was our statement. Then x is a multiple of the identity. Isn't it trivially true that if x is 0, then x also obeys this? 0 times t1 is t1 times 0. That's trivial, right? When I say 0, I mean the 0 map, the null map. Isn't that trivial? Then why didn't I say x is a multiple of the identity or 0?
Well, you can take the constant that you're multiplying with the identity to be 0.
Right. So the null map is also a multiple of the identity. So I don't have to say that separately. Okay. So fine. So this, of course, as we stated it, these are results in linear algebra, not really results in group theory. The reason why we spend so much time on the Schur's lemmas is that we are going to use them to prove various important results in group theory. Some of these results you have seen in the previous course, some you haven't. So all of them are going to be very, very important. So that's for Thursday. Okay? Okay, not for Thursday, for the rest of the days, because Thursday we will just talk about the great orthogonality theorem. Okay, I'm done today. Any questions? Or you may have already had enough. So if there are no questions, I will stop the recording.